Welcome back. This is the final homework problem from homework number 3. Homework number 8 is problem number 3 on homework number 8 on entropy stuff, entropy analysis. So efficiencies, that kind of thing, but also feasibility. So, and this is a feasibility problem. It's asking, okay, what's the final temperature and pressure of this system? And is this even possible? Okay, and the is this possible is based on an entropy, energy, and mass balance. Okay, if those are all come out the way they're supposed to, then it is possible. Okay, so what we have, I've already drawn the picture. I'm going to draw my boundaries in a sec. Okay. Okay, so what we have, at the beginning of the system is, we have 500 degrees Celsius, 10 bar, and a certain heat capacity for this gas A. There's a latch here, and then we have gas B, which is also at 1 bar, but 100, well, it's not also 1 bar, it's at 1 bar and 100 degrees Celsius. It has a temperature-dependent heat capacity. The piston is initially at 10 centimeters here, so it's 20 centimeters from this wall. Who knows what the area is? I don't think it will matter, but we'll figure that out. Okay. They're both ideal gases, and so first off we have to figure out what's the final temperature and pressure of this system. Okay. And so really what we need to do, well, we'll get there, but we need to find the final temperature and pressure of the system and then figure out, is this even possible? Okay, so let's make some assumptions. Let's assume, okay, and so we're going to draw our boundary this way. Okay, the reason we're going to do that is so we don't have to worry about the work being done internally. Okay. Again, we could figure it out, internally, but we don't need to work, figure it out internally. Okay. I don't believe we do. Maybe we do, but I don't believe we do. Okay. Because the work that A does is going to do the work on B, and so I think it's going to be a net loss. It's going to be a net loss of 0 anyways, and it won't really affect or matter. Now, what there is going to happen is there is going to be heat transfer, but not between the systems. So we're going to assume that this, within a boundary drawn this way, that it's adiabatic. Okay. We're also going to assume that there's no work. Okay. Within, across the boundary. Again, we're looking at the boundary here. The boundary is so important in a problem like this. Well, it's important in every problem, but this really illustrates why an appropriate choice of the boundary is important. Okay, we are going to assume an ideal gas. We're going to assume at least, a heat capacity of A is constant. Okay, so we'll assume that. We won't assume the other one, but we will assume that one. Let's see here. We don't care about kinetic energy or potential energy. Okay. Let's see here. It's technically a closed system, so nothing's coming in, nothing's coming out. Closed system. Okay. Let's see here. Adiabatic, no work. Ideal gas. Okay. Yeah. So the first thing, we should at least do. We will need to figure out the final temperature and final pressure. But let's at least do our full analysis first. Obviously, there's going to be missing information in terms of temperatures, pressures, and all that good stuff. But let's do our full analysis first to kind of get a sense of what does our mass, our energy, and our entropy balance tell us. Okay? So let's move forward with that in mind. Okay, so mass balance, or mole balance in this case. So we got in minus out equals dn dt. That was one wonky d. CV. That goes to 0. That goes to 0 because it's a closed system. and I did assume a closed system, which means that dn dt of the control volume is equal to 0, which means that n2 minus n1 is equal to 0, which means that my moles of my whole system does not change. Okay. Now let's do our energy balance. N dot I H I plus 1/2 E squiggly squared I plus G Z I minus summation of N dot E H E plus 1/2 E squiggly squared E plus G Z E plus Q dot plus work dot equals D capital U plus EK plus EP. CB. Alright. So, nothing coming in, nothing coming out. No heat, no work, no kinetic energy, no potential energy. We have capital DU dt CV equals 0. Okay. Which means that capital DU is equal to 0, which means that n2 U2 minus N1 U1 is equal to 0, which means N U2 minus U1 is equal to 0, which means U2 equals U1. But because this is an ideal gas, that means T2 is equal to T1 of the system. Okay. And so, in this case, so now this is for the overall. Now, if we did an individualized, what we would find is like work plus Q, because there would be heat transfer between the two systems. Work plus Q would equal the other one. Okay, would equal our delta U. And we may need that. I'm not going to rederive that in case that is how we want to approach this problem. We're going to assume, now, the temperature as a whole, the average temperature. So really the average temperature is kind of based on, the kinetic energy of the molecules. So there's kind of a molar situation here. So it is based on it's based on we have to find an average temperature based on the amount of moles of each system. Okay, because the more moles it's going to have, the more kinetic energy it's going to have as a whole. Okay, it's really where we're going with this. Okay, so now let's look at our entropy balance. Now again, we may need to analyze this system from a individual system perspective, but for now we're going to assume that it doesn't matter. But again, it might. Okay. And that's the whole point of an assumption, is that sometimes you have to go back and do redo your analysis based on what you see and what you don't see. Okay. But now let's look at this. Let's look at the system from the perspective of Okay, now let's look at the system from the perspective of entropy. And so we have we have S dot gen is equal to summation of exits M dot ESE minus sum of inlets N dot ISI plus, minus sum of our heat transfer, T surroundings, plus ds dt control volume. Okay. Again, we're looking at the system as a whole, so nothing comes in, nothing comes out, no heat transfer is occurring, and so I don't care about time, so my total S generation is equal to my, change in entropy of the whole system. Okay, which is going to equal, N2 S2 minus N1 S1, which is going to equal N S2 minus S1. Now, we've already established that as a system, as a system. This is isothermal. And so all this really is, you know, how does the pressure change as a system? So I'm thinking now we do have to address this as separate systems, unfortunately, okay? Because we don't know how the pressure's really changing. You know, we don't really have an initial pressure associated with this. Okay, so really we do want to approach this as separate systems with work and heat, and so our energy, mass balance will still be the same. I'm not going to go through all the steps of the energy balance, but how the energy balance would simplify is for each system you would have Q plus work equals the moles of the system, so we'll just put I, and we'll put this as I. Well, the heat and the work are they're going to be exactly the same, they're just going to have different signs. So we have I doesn't work. Okay, fine. N of A, and we'll just have 2. So NA of U2A minus U1A, okay, which is going to simplify down to NA CVA dt, okay, from T1 to T2. The T2 is the same, but the T1 is different, okay. And then the other one is going to be minus Q minus work, because whatever work's done on one is going to do it on the other, and the heat's the same way, okay. And then our work is going to be equal to minus P dV, okay. This is going to be an ideal gas, okay. Pressure changing, temperature's not constant, volume's changing. I don't know if we can do that, so we're going to have to probably just keep our work as work. Okay. But this is going to basically be the same thing. We're going to have NB, an integral of CVB from T1B to T2 dt. Okay. And then from an entropy balance perspective, it is basically going to be the same thing. I'm going to have my heat transfer. Now my T surroundings, I'm going to have my T surroundings, which is going to be the other one. Okay. And so I'm going to have basically ST gen of A, okay, the total entropy generation from system A, okay, and that's going to equal, minus Q divided by, see, that's a tricky thing. Which temperature do we really use? Do we use the 500? Do we use the 100? Do we use the average? I'm going to say in this case that the most appropriate one to use would be the others, would be like whatever that temperature is. Okay. So I think, that's kind of tricky, and that's probably going to play into the feasibility. Okay. So we're going to say, basically, the T1 of B is, the heat transfer, okay, that's associated with that, plus NA of, S2, which is going to, S2A, we'll plug in what delta S is here, so we're going to have integral of T1A to T2 of CV over T, CVA dt, minus R natural log of P2 over P1A, okay, and then the other one is going to be ST gen of B is going to equal Q over T of 1A, because the minus times the minus, okay, plus NB T1A to T2A, T2 CVB over T dt minus R natural log of P2 over P1B. Okay. Oofda. Now, that still doesn't really tell us what's the final temperature and what's the final pressure. But again, we're kind of assuming, we're assuming an average here, okay? And so what we need is, so first off, we need to figure out what NA and NB is, okay? So NA is equal to PV total A over 1, P1 over RT1A, okay? So I know the initial pressure, I don't know the initial volume, but what I do know is kind of like this height. So NA is basically equal to P1A times the area, okay? And I think my areas are going to cancel out, okay? Times kind of like my height 1 of A. We'll call it width. Width seems better. 1A over RT1A. Okay, so now I have an NA based on the area. Same thing with B. Okay. P1B, A width of 1B over R2T1B. Okay. And so if I want kind of the final, okay, let me erase some of this. Okay, so really I need to find the final temperature and the final pressure. So, and how I want, so what I'm going to do is I'm just going to write this as P2 over T2 is going to equal my N whatever it is, R over V2 total, okay. And so I'll have two equations. I'll have P2 over T2 equals NA, which is this guy. Let's, I guess, write that. Okay, so my areas are going to cancel out because I'm going to have this V2 total. The area on this one is going to divide by the area on that one. So I'm going to be okay, but let's just write it out anyways. I'm going to have P1A R over... so my R's are going to cancel out too. T1A, okay, times my width, okay, width 1A over over width 2A, because that's going to be my volume there, okay. And so I have. So I know, I don't know, okay. And then I need a final one that's width equals width 1A plus width 2A. Now I have enough equations, enough unknowns, because P2, T2 also is going to equal P1B with 1B over T1B with 2B, but I know the total width, and so the difference is there. So I have enough to get my temperature and my pressure exactly, okay, and the final position, okay. Now, so I have enough to get that, okay. So that means I have my NA and I have my CV delta T, okay. And I have my CV delta T there, and I have my NB. Okay, so I don't know my Q, I don't know my work, okay, and I don't know my ST gen A, and I don't know my ST gen B, okay, so I have 1, 2, 3, 4 unknowns, and 1, 2, 3, 4 equations. I have enough to solve for everything, technically, okay. Is it a chore? Absolutely. But I do have enough to technically calculate for everything. Now, I'm not going to, for the sake of time of this video, but I do have all my unknowns, enough unknowns and enough equations to figure this out. what the question's going to ask. Now, it says the total entropy generation of the universe. Well, that means I need to add up my ST Gen A and my ST Gen B. Okay, that will give me my total entropy generation of the universe. Now, what I really need to ask at this point is, okay, I have my ST Gen total, okay, is it positive? If it's not positive, then this doesn't happen. Now, if it's 0, then it's okay, because that just means this is a reversible system. Okay, and I doubt it is a reversible system, but you never know. Okay, but if this is not a reversible system, if it is negative, it means it cannot happen. Okay, but you have to do all the number crunching to figure that out, and you, as you can see, that's a lot of number crunching. So, but I will leave that to your own devices. That's how you do the approach and all the equations associated with it.